This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1,000,000 miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4-meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
Thank God.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you. Shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail-biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1,000,000 miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet. Then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sun shield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sun shield layers of approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2 thousandths of an inch thick. Making them go where you want them to go in zero-G is extremely challenging.
The sun shield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sun shield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sun shield under control as it unfolds. First, we release these special restraints that protect the sun shield during launch. They roll out of the way, but not all the way until we are ready to deploy aside. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sun shield release mechanisms need to fire on cue. 107. They free the 5 sun shield layers, allowing them to extend as the mid-booms deploy.
Sun shield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, the secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
on stellar structure and evolution. Into the terms that we use for them today: spirals, ellipticals, and irregulars, kind of fuzzy things that don't have defined shape, but we know that they're still bound together. What have their namesake telescopes taught us? So this is a set of pictures. We've got all light together. We've got light from Hubble, X-rays from Chandra, and infrared from Spitzer. In 1054, when humans first saw the Crab Nebula, they described it as a new star, a stellar nova, something that came from nowhere and was there for a while and then disappeared. And we've now identified it as a remnant of a supernova explosion. In the lower left image is a Chandra picture in X-rays, and it gives us a new view into the heart of the nebula that was left behind after the supernova explosion. And it reveals details about the area around the central pulsar, that degenerate matter that is spinning very rapidly. And by observing it in the X-ray band, we've been able to see particles moving and clumps moving in the rings around the pulsar for about 20 years. But we see it differently when we look at the purple Hubble image or the pink Spitzer image. And then when we combine all of this data into a single picture, that very colorful one in the upper left, we can begin to understand how jets of matter and antimatter are shooting out from the north and the south poles of this pulsar, and they are interacting with the interstellar media around it. And these features are driven by interactions from the rapid rotation and the magnetic field of the pulsar and the generated electromagnetic fields. Now, the Crab Nebula is also referred to as M1, and you'll see M in a number in a few of my slides. M stands for Messier, and Charles Messier was a comet hunter, and his catalog of fuzzy things that weren't comets is kind of one of those great lists for observing with a small telescope. There are two ways you can find comets. You can go out and identify a comet, or you can eliminate all of the things that aren't comets. And what's left is comets. Charles Messier went that way. It's kind of a hard way about it. But it is a spectacular catalog of things to look at. A planetary nebula represents the phase of stellar evolution that a star like our sun will eventually go through in a few billion years. And a star like our sun uses up all of the hydrogen that it has available to burn in its core, and then it expands into a red giant, kind of this swollen body. And in this phase, it's going to lose most of its mass. It's going to be floating out around it. And then the rest of it will collapse down to a hot core that is a white dwarf. Fast winds emanating from that core will ram into the layers of lost atmosphere from that original star, push it outward, and that creates kind of these filaments and the structure that we see in the middle Hubble image, in the bands that our eyes are familiar with, that you might see through a fairly powerful telescope. But as you can see in the Chandra images on the right, about half of the planetary nebula have X-ray point sources in their centers. And some of those also have high energy sources that indicate that there's two, that there's a companion. And this is telling us things that we would not know if we weren't able to combine images and information from two different wavebands of light. Drop page. The Sombrero Galaxy, another M104. So this was taken by both Spitzer and Hubble. They joined forces to image it together. And we get the striking composite here on the right. And it's a fairly popular site in small telescopes. And it's called the Sombrero Galaxy because in the visible light, it really does kind of look like a broad-brimmed Mexican hat. But if we look in the Spitzer image down there, you will see that it looks more like a bullseye. So the Hubble visible light image, we only see the near rim of dust in silhouette. But the recent observations with Spitzer show that there's a bright, smooth ring of dust encircling the galaxy, and then there's this halo and a disk set of stars that would not otherwise have been able to see because they're obscured by the dust. And in the full view from Spitzer, if we could get a little bit more detail on it, we'd see that the disk is warped. And so there's probably been some interactions between this galaxy and another galaxy. And there's some clumps that indicate that there's some stars forming. So it is a much more dynamic picture than we get just from the visible light. Here we have the Pinwheel Galaxy, M101, in a series Chandra, Hubble, Spitzer, and then combined again into a multicolor image. Each wavelength region shows different aspects of the celestial objects. In the composite in the upper right, the red color shows Spitzer's view, the infrared. It highlights the dust lanes in the galaxy where stars can form. The yellow color, which is Hubble, shows visible light, and this light comes from those stars. And they trace the spiral structure similar to the dust lanes. And then the blue color shows us Chandra's view in X-rays. And sources of X-rays can be gas heated to millions of degrees, can be exploded stars, and materials colliding around black holes. So there's less of it overall, but it is very bright, and it tells us things about the galaxy we would not see in the other bands. And imposing these images one on top of another allows astronomers to correlate features. How does dust and stars go together? Are there black holes in different places? The James Webb Space Telescope represents the next generation of space telescopes, a successor to Spitzer and eventually the follow-on to Hubble. Working primarily in the infrared bands, Webb carries on the legacy that Spitzer started. And it views through the universe through different light than Hubble does. And it has a 6.5 meter, about 21 foot diameter mirror that dwarfs its predecessors and allows it to see farther in distance and further back in time. So this is a Spitzer image taken with the 3-foot Spitzer mirror. And you see newborn stars beginning to peek out from underneath a blanketing layer of dust in the row of Fuci that would be in the constellation of Fucus, a dark cloud of dust. Imagine what a telescope about 1,000 times more powerful could show us about this star formation region. In fact, until 2002, what we are calling today the James Webb Space Telescope was called the Next Generation Space Telescope. And it was in 2002 that NASA named it after James Webb. He was a Marine Corps veteran with a long career in public service. He was even Deputy Secretary of the Treasury and Undersecretary of State for Truman. But under his direction, NASA took on their most ambitious project. He's only the second administrator, but the Apollo program that launched a man on the moon to the moon in under a decade to meet President Kennedy's objectives, that was a significant challenge. And James Webb took that announcement and he went with it and he cajoled and he did all of the backroom deals that you would expect from a Washington insider and a career bureaucrat, and he brought it to fruition. And Apollo got to the moon on time and was great for national prestige and also opened a new world of science. But James Webb didn't just do this. At the same time, he believed that NASA needed to balance human spaceflight and the engineering challenges with doing science. And so during his time, at the same time they were trying to launch the moonshot, 75 other probes, robotic programs, spaceship were also launched and sent to understand the solar system, something mankind had never done. Our first views of Mars and Venus as worlds unto themselves. Our first look at the region outside of our own Earth's atmosphere. And of course, lunar missions that allowed the astronauts to operate in that environment safely. The telescope named after him will continue that legacy of exploration. So changing gears, why infrared light? The rainbow of light that our eyes can detect is only a small portion of the overall electromagnetic spectrum. The telescopes can be engineered to look at shorter wavelengths and longer wavelengths to reveal the universe in ways that we might not experience on our own. And Webb works in the near-infrared and the mid-infrared ranges, so just beyond the light that our eyes can detect. And by just beyond, it's just beyond red, so longer than our eyes could see. But let's look at the electromagnetic spectrum in greater detail. So there's the portion that is labeled visible, and that's the colors of the rainbow. It's what our eyes detect. Fireflies, light bulbs, stars all emit visible light. Beyond the red side of the visible spectrum, wavelengths are longer than the human eye can detect. And this is what we call infrared. Night vision goggles pick up infrared light emitted by you, our skin, and other objects with heat. In space, infrared light helps us see through the dust to stars that could be hidden there. Even longer than infrared are the microwaves that cook your popcorn in just a few minutes, but are also used by astronomers to learn about the structure of nearby galaxies. The longest are the radio waves. They bring us your tunes when they're emitted by a nearby radio station, but the radio waves are also emitted by stars and gases in space. If we go to the other end and look just shorter than what our eyes can see, beyond violet, Roy-G. Biv, red, orange, yellow, green, blue, indigo, violet, ultraviolet, then this is the light that the sun emits that causes your skin to burn and to give you a tan. But hot objects in space also emit UV or ultraviolet light. And even shorter are the X-rays that your dentist may use to image your teeth, or a doctor may use to look for a broken bone. And airport security uses to check what's really in your bag. And in addition, there are hot gases in the universe that emit X-rays. And shortest of all are the gamma rays. And in some cases, doctors may use these for imaging your body. But the biggest gamma ray emitter of all is the universe itself at cosmological times. So the longer wavelengths, such as infrared, are able to pass through areas of dense gas, dust. They're just kind of longer and they don't even notice that blockage. Shorter wavelengths, including ultraviolet light, can get trapped in gas and dust, which means that telescopes that specialize in visible light don't capture them either. These mosaics of the sky were taken by telescopes specializing in visible and different bands of infrared light. The familiar visible image on the left, owing to the strong obscuration by interstellar dust, we see primarily stars within a few thousand light years of the sun. But that's pretty small compared to the overall size of the Milky Way, which has a diameter on the order of hundreds of thousands of light years. And as we see nebulae of hot, dense gas that are widespread in the image, and the dark patches that are dust features. The middle image uses near infrared, so very close to what our eyes can see, but a little bit longer. And most of the emission now is from cool, low-mass stars in the disk and the bulge of the Milky Way. Interstellar dust does not strongly obscure emission, so we're seeing beyond that dust, and we can see all the way through the galaxy at this point. The images on the right uses the longer infrared, and most of the emission now is thermal. It's interstellar dust that has been warmed by starlight. And it includes star-forming regions in the interstellar clouds. But let's look at this in a more familiar object. I found a little mouse. Visible light provides us with detailed information about environment. It's got color and texture. So we've got a brown mouse, we can tell he's furry. And in infrared light, we see different details. The mouse glows dramatically. That's a pretty striking picture. And you can play with the infrared camera that we have in the back later and see some of these features for yourself. And some parts of the mouse are warmer than others, so we can see that variation in this image. So everything is glowing, even if we can't see it with our eyes. So we can see, if we had an infrared camera, we could detect my computer, we could detect you. Hopefully we don't have any mice to detect. So the James Webb Space Telescope is going to see the universe in this infrared light that's invisible to our eyes, and we might experience as heat. And firefighters use infrared cameras to see and rescue people through the veil of smoke. So invisible, we don't know what's going on. In infrared, we can see that there is someone in distress. Stars and planets form inside of thick dust clouds, and so peeking inside could lead to exciting new discoveries. James Webb will also be able to see objects like the first galaxies that are so far away that the expansion of the universe has stretched the light that they emit from ultraviolet and visible bands into the infrared. By specializing in infrared light, Webb will be able to see what's beyond this dust. The Carina Nebula here was captured by Hubble in visible light on the left, and also Hubble can see a little ways into the infrared, although that's not its specialty, so there's also a near infrared image of the Carina taken by Hubble. But Spitzer and Webb focus on the infrared and going beyond the dust. In the visible light, we see streamers of hot gas that are flowing off the ridges of this structure in the Carina Nebula and thin veils of gas and dust, illuminated by starlight. This gives us the towering peaks that kind of looks like a fantasy landscape. And this is driven by giant young stars. In the near infrared, though, we begin to see far more stars. All of the densest dust has been cleared away from our view. And so the young stars that were hidden in that dust are now out and visible where we can study them. And so Webb's images will help us see even better through these clouds and figure out what's going on in these dense areas to understand how stars are born and begin to evolve. So when we talk about the expanding universe affecting light, we're talking about an effect known as cosmological redshift. And red probably wasn't the right color to use, but redshift seems to belong in red. And as light travels through the universe, its light is just stretched as the universe expands to longer wavelengths. So if we imagine that light is coming from a star to the Earth, because light has wave properties, it kind of fills that whole space. If the universe expands between us, then that light wave is stretched. Longer wavelengths moves from visible light that our eyes can see into the infrared that we need something like the James Webb Space Telescope to see. And this is the light that James Webb is going to capture This is the light that will allow us to see the most distant galaxies. I've got other pictures. Okay, one more picture of nebulae because I like pretty pictures. And so this cosmological redshift means that more distant objects and consequently older objects can come into view. This is because we kind of equate age and distance in astronomy because we see things not as they are this moment, but as they were when the light coming from them left them. So the further something away is, the longer that light has taken to get to us, and therefore the older it was in our perception of it. So we see objects not as they are, but as they were. And the most furthest objects from the Earth can be billions of years old, going back to the first galaxies, the first stars. So here, the Hubble image on the left is the Monkey Head Nebula, because I kind of think it looks like a snail, but at any rate, I'm told monkey head. And it's a star-forming region. Again, in visible light, we see the shaping of the pillars from the embedded stars. And when we move to the infrared light, more of the stars that were in that dust cloud are visible. But we also begin to see more distant galaxies that were not obvious in the visible range, bringing into view things that are further away and older, that we cannot see with our current technology. So this brings us to all of the questions that we could be asking as we think about James Webb launching. What was the universe like after the Big Bang? What are the characteristics of galaxies as the universe ages over billions of years? What more can we learn about how stars are born, live, and die? And Webb can see through dust. What will it reveal about planets and stars forming and their relationship to one another? And these are only a few of the questions that we are thinking about and planning to ask and answer through the James Webb. But probably the most exciting things are going to be the things that we didn't think to ask, because a new window on the universe has opened. The science that we expect to be done with the James Webb Space Telescope will bring us closer to NASA's kind of overall goal of discovering the secrets of the universe and searching for life beyond Earth. And wow, those are some pretty big, awesome goals. It's what gets me up in the morning. Well, night. I became an astronomer, so I didn't have to work days. And I'm sure that you would like to ask more questions about this and know more about the potential for James Webb and the engineering that is allowing us to achieve these goals. So at 3:30, Dr. Young, a NASA postdoctorate fellow who works in the Observational Cosmology Lab at Goddard, will be here to tell us more about the James Webb Space Telescope and using it as a time machine to see further back into the history of the universe. And as I said in kind of the stalling for time earlier, this event is brought to you by the Friends of Arlington's David M. Brown Planetarium in conjunction with NASA. And we are so glad that you could join us. We are trying to, while the planetarium is closed for construction, bring you some of the science and outreach and enrichment that cannot be done in that facility. We are also continuing to do online events for those who are uncomfortable coming to in person and find the balance that serves Arlington best. While this event is free to attend, it's not free to host. So consider a membership that will support future programs. Recordings of many of our events, as you can tell, we are accommodating those for online, are available on our Vimeo and YouTube channels. So you can catch things that you might have missed. And to find out when and where our next event will be, please follow us on social media. Thank you so much for being here, and we'll have another speaker in a bit. And in the meantime, check out the activities in the back. Thank you.
I encourage everybody to come.
The Hubble Space Telescope and the James Webb Space Telescope will complement each other in the study of celestial objects. They are different sizes, will be at different locations, and have different instruments that cover different wavelengths. But together, they will help answer some of the most fundamental and inspirational questions that we have about our universe.
The James Webb Space Telescope is impressive. It's 3 stories tall, as wide as a tennis court. It's got a 21-foot primary mirror. And then it's got these 4 instruments that are just incredibly powerful. It's the largest, most technologically challenging space telescope ever created. It's 100 times more powerful than the Hubble Space Telescope, but at half the weight. It's designed to look back in time, even further than Hubble, to see the very first galaxies to form after the Big Bang. Building Webb is truly a feat of innovative engineering. Each material must survive the turmoil of a launch and the varying temperatures of space. And it all starts with the elements. James Webb Space Telescope. There's a lot of hustle and bustle because the integration is in full process. Just look at NASA's James Webb Space Telescope. Its gold mirrors are definitely its most stunning feature. And yeah, that's real gold. Humans have a long history of searching for gold and using it in their most prized possessions. These mirrors weren't gilded to make them pretty. There isn't even all that much gold, about 5 men's wedding rings worth over the 18 mirrors. So I wanted to see for myself, why does it make sense to use a microscopic layer of gold on these mirrors? So our everyday mirrors tend to use silver or aluminum as their reflective material. One of the major differences between our earthly mirrors and these fancy optical mirrors is the position of the reflective material. Look at the side of this small mirror. It has the glass in the front and the metal coating behind it. That glass actually traps a tiny amount of light and creates what we call a ghosting effect. So the clearest reflection that we can actually have has the metal coating on the front. Dentists and hygienists also use front surface mirrors to get an accurate look at your teeth. The position of the reflective coating might make a sharp observation, but the kind of metal also matters too. There are a couple of reflective materials that really excel at reflecting infrared light, which is how Webb will observe. Aluminum reflects 85% of that wavelength of light. Silver, up to 95%, and gold, up to 99% of all the infrared light that it encounters. But gold is special, and I can show you using the rings that I typically wear. This one is gold, and this one is made out of silver. And in the presence of the right chemicals, these 2 materials react differently. I think actually it's a little easier to show kind of all of this with this spoon. My mom surprised me by pulling out this whole tub of silver. Not tub, it came out of a box. So I'm able to demonstrate sort of on a bigger surface here how silver can react differently using an egg. Smush that in. Got nothing. We've got nothing. So what we have is a really fast reaction between the sulfur in the egg and the silver, and it creates a new thin layer on the spoon of silver sulfide. Silver might be great at reflecting infrared light, but it tarnishes so easily. Not only does gold reflect more infrared light, but it is also one of the most unreactive metals. It is too durable to oxidize and decay in space, and it is certainly Webb's best chance at seeing the cosmos.
The more distant in space we look, the further back we're looking in time. And so we're designing the James Webb Space Telescope to see past the point where Hubble could see, and to see the very first stars and galaxies to light up after the Big Bang. The James Webb Space Telescope is designed as an infrared telescope because infrared is really where the key science questions will be answered. To see those very, very distant galaxies, the light from those galaxies has been redshifted. The expansion of the universe sort of stretches space-time. The light from the galaxies gets stretched as well. And so longer wavelengths of light are redder. And so at some point in the very distant past, the light from those galaxies has been shifted, redshifted, all the way out of the visible spectrum to the infrared part of the spectrum. So having an infrared telescope in space is one of the things that's going to allow us to see those very first galaxies. One of the key things that the James Webb Space Telescope is designed to do is detect the very first stars and galaxies that were born in the very early universe. So this is a part of the universe that we haven't seen at all yet. We don't know what's there. The more distant in space we look, the further back we're looking in time. With Hubble, we're able to push back and see pretty far into the distant universe, but we do reach a limit. And so we're designing the James Webb Space Telescope to see past the point where Hubble can see, and to see the very first stars and galaxies to light up after the Big Bang. We know that there is a time in the universe's past where the galaxies were the first to light up. Basically, the stars and the galaxies send out ionizing radiation, which clears out the fog of the hydrogen in the universe. And so once that hydrogen fog is cleared out, then the stars and galaxies can shine through. And so getting to that point, just beyond what we call the dark ages, is one of the major goals of the telescope.
Mirar el pasado remoto, mucho más remoto. Si miramos hacia atrás, allá por la década de 1920, Edwin Hubble descubrió la expansión del universo al observar los movimientos de las galaxias lejanas. El telescopio espacial Hubble ha ampliado este límite de nuestro conocimiento sobre el pasado, observando galaxias aún más remotas y viendo incluso más atrás en el tiempo. Pero el telescopio Webb puede llegar aún más lejos, a las primeras fases de la vida de una galaxia. Como un niño que está creciendo, la etapa de mayor desarrollo de una galaxia ocurre durante su primera etapa. Nudos de estrellas y gas comienzan a transformarse en la figura completa de una galaxia madura. Con Hubble podemos observar la adolescencia temprana del universo a medida que las galaxias crecieron, pero Webb podrá fotografiar la niñez, que nos mostraría mucho más sobre cómo surgió el universo. Actualmente, el telescopio espacial Hubble está sobrepasando los límites de capacidad de detección tan atrás en el tiempo como es posible. Pero el telescopio Webb está diseñado específicamente para encontrar ese momento especial de la historia inicial del universo. Al estar equipado con la última tecnología, Webb nos permitirá ver los objetos que trajeron luz al cosmos y develar los misterios de la reionización. Solo entonces tendremos una mejor idea de cómo el universo se convirtió en lo que vemos hoy a nuestro alrededor.
Si el propósito de un telescopio es traer cosas lejanas más cerca a nosotros, entonces ¿por qué enviamos algunos de ellos tan lejos? La principal razón para colocar un telescopio en el espacio es para evitar ese perpetuo problema, la atmósfera, ya que los astrónomos no han descubierto cómo deshacerse de ella, y es una verdadera molestia. En primer lugar, la atmósfera simplemente se interpone en el camino, con sus nubes y humo y neblina que pueden bloquear la luz de estrellas distantes o planetas cercanos. E incluso solo el aire en un cielo despejado bloquea una enorme gama de longitudes de onda de la luz, prácticamente solo dejando pasar la luz visible y una pizca de infrarrojos y ondas de radio. La atmósfera también, ¡hey! ¡Ya basta!, nos distrae. De día, la luz visible que llega desde el Sol rebota en moléculas de aire y otras pequeñas partículas y supera completamente la luz de cualquier otra estrella a la que quieras observar. De noche, la luz que llega desde la Luna y desde fuentes humanas rebota en las mismas partículas, lo cual opaca la luz de las estrellas y galaxias más distantes y apenas visibles, debilitando sus imágenes. La atmósfera también arruina las cosas. El aire está en constante movimiento, y justo como los espejismos, esta turbulencia desenfoca y distorsiona la luz de las estrellas, causando que éstas parpadeen y que sus imágenes en telescopios sean borrosas. Podemos evitar todas estas molestias colocando telescopios por encima de la atmósfera, en el espacio. Además, hay otros beneficios. Un telescopio espacial puede hacer observaciones las 24 horas del día. Un telescopio espacial puede colocarse lo suficientemente lejos del calor infrarrojo terrestre y luego enfriarse lo suficiente como para tomar claramente imágenes infrarrojas. Y un telescopio espacial es un telescopio que colocamos en el espacio exterior. Claro, hay algunas desventajas con los telescopios en el espacio. Es difícil y costoso enviarlos allá, difícil y costoso repararlos si se averían o si quieres actualizarlos con partes más nuevas y sofisticadas, difícil y costoso llevar a personas de tour, pero en serio, ¿cómo puedes discutir con esto? Y esto, y esto, y esto, y esto, y esto, e incluso esto, y esto, y esto, esto también, y esto. Muchísimas gracias por vernos. Este video fue posible gracias al proyecto del telescopio espacial James Webb en el Space Telescope Science Institute, donde colocan telescopios en el espacio para que no tengas que preocuparte de cosas como las nubes y la lluvia. Gracias de nuevo por vernos, y gracias al proyecto del telescopio espacial James Webb por ayudar a hacer posible este video.
¿Cómo descomponen la luz los telescopios espaciales? ¿Recuerdan los colores primarios? Cualquier otro color se forma mediante la combinación de los colores primarios, rojo, amarillo y azul. La luz también tiene colores primarios y funcionan de la misma manera. Los televisores usan los colores de la luz para crear las imágenes que vemos. Cada píxel de la pantalla del televisor contiene una cierta cantidad de luz, roja, verde y azul. La cantidad de cada luz que compone el píxel determina su color general. Entonces, cada color en el televisor proviene de una combinación de los colores primarios de la luz, rojo, verde y azul. Las imágenes de los objetos celestiales que proyectan los telescopios espaciales son también una combinación de los colores de la luz. Cada píxel se puede descomponer en sus colores de base. Para descubrir aún más, los astrónomos descomponen la luz roja, verde y azul en secciones más pequeñas denominadas longitudes de onda. Esta descomposición se llama espectro. Con la tecnología apropiada también se puede medir cada píxel de luz como un espectro. Las imágenes nos muestran un gran conjunto, mientras que los espectros nos revelan los detalles más sutiles. Los astrónomos usan los espectros para aprender cosas nuevas, como qué moléculas hay en las atmósferas de los planetas y en las galaxias lejanas. Una unidad de campo integral, o IFU, por sus siglas en inglés, es una herramienta especial en el telescopio espacial James Webb que captura imágenes y espectros al mismo tiempo. La IFU crea un único espectro para cada píxel de la imagen que captura el telescopio, lo que ofrece a los científicos una enorme cantidad de datos valiosos y detallados. Entonces, con una IFU obtenemos una imagen, muchos espectros y un mayor conocimiento de nuestro universo.
How can infrared light see through cosmic dust? To study the formation of stars and planets, astronomers look at the giant clouds of molecular gas and dust where new stars are still being born today. But when we turn our most powerful tool, the Hubble Space Telescope, on these clouds, we see mostly shadow. All that gas and dust cloaks the stars, blocking their light. But not all of their light. Visible light, the kind we see with our eyes, can't get through. But infrared light is different. Its wavelength penetrates gas and dust. The infrared detecting instruments on NASA's James Webb Space Telescope will capture infrared light as it emerges from the cloud, creating images that look through the gas and dust to reveal the warm, bright objects within. With Webb's help, we will be able to see both the newly forming stars and the disks of debris around them that eventually coalesce into planets. Webb will even detect newborn planets cocooned inside these disks.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope.
The Webb Telescope is NASA's biggest and most powerful space telescope ever. It's going to help reveal our universe like never before.
Delta, what do you think we'll discover?
I think we'll see stars, planets, and galaxies. I can't wait!
NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb Telescope will find. It could be a drawing, a poem, a song. You could be creative.
I drew a picture of what I think the telescope will see. This is the telescope, and these are our planets and stars.
Wow, Delta, it's beautiful. I can't wait to see what everyone else comes up with. You can share a photo or a video of your art and what you think Webb will discover using the hashtag #UnfoldsTheUniverse.
Go, Webb, go!
Constructing the James Webb Space Telescope, a mission led by NASA with its partners, the European Space Agency and the Canadian Space Agency, requires the collaboration of thousands of people from across the United States, Canada, and Europe.
The James Webb Space Telescope is the most ambitious and complex space science mission humanity has ever undertaken. Webb is NASA's highest priority science mission.
This is the optical and science segment of the Webb Space Telescope, in one of the largest clean rooms in the world at NASA's Goddard Space Flight Center in Greenbelt, Maryland. This half of the observatory element successfully passed a series of rigorous vibration and acoustic tests to ensure Webb's optics and science instruments can handle the stresses of launch. This element was packed and transported to the Johnson Space Center in Houston, Texas, for cryogenic testing inside its massive test facility, simply called Chamber A, a National Historic Landmark for its work during the Apollo missions.
Successfully completing the optical telescope element was a significant milestone. And now we look forward to completing final tests of the spacecraft element, and then integrating both halves into the observatory.
To give you a sense of where we are in the mission, the Webb Space Telescope consists of two main segments: the spacecraft bus and sunshield, called the spacecraft element, and the iconic 6.5-meter telescope and science instruments, called the optical telescope element. Today, both halves of the Webb Space Telescope are at Northrop Grumman in Redondo Beach, California. Here, the most advanced space telescope optical element will be integrated with the spacecraft element, which includes the tennis court-sized 5-layer deployable sunshield and the spacecraft bus, where the Webb's data and attitude control systems reside. The sunshield protects the telescope's optics and science instruments from infrared radiation, or what we feel as heat, emitted by the sun, Earth, and Moon. Each thin sunshield layer is about 1/1000th of an inch thick and coated with reflective aluminum and protective silicon to provide sun protection of SPF 1 million. Webb is a testament to innovation. Intricate and advanced technological systems were developed to enable awesome science discoveries.
The James Webb Space Telescope is the most technologically challenging observatory we've ever built. No one's ever done anything like this before, but the science will be worth the wait.
Webb will conduct a breathtaking array of science investigations across the history of the universe, ranging from searching for the first distant galaxies to light up after the Big Bang, to searching for the building blocks of life in atmospheres of exoplanets.
The observatory's capabilities are so enormous that major advances are expected across every branch of astronomy.
We're pretty distant. All right. I hope if I do that, my voice will come through more clear. And hopefully that will help. So Kathy, should I start now? Anytime? All right. Hi, everyone. I'm Aaron Young. I am from the NASA's Goddard Space Flight Center, and I'm here to tell you all about the James Webb Space Telescope and how it is actually a time machine. So before we get there, we have to figure out how it works first. And then also, I'll tell you a bit about the history of putting up Space Telescope. Why do we do that in the first place? And then what can James Webb do? And then I'll jump over and talk about how the universe works, because that's also important. We're going to use the telescope to look into the universe. And then we put the two things together. I tell you how James Webb Space Telescope can help us look into the universe, but also look back into its past. It's a time machine again. We have to use it to study the past of the universe. And then at the end, I will tell you the all exciting part, like how it works, how it deploys, how it flies to the second Lagrangian point. It's going to be so much more far away than the Hubble Space Telescope, and then how it works there as well. All right, so here comes the history part. There's a long history for us to put things in space, as I mentioned. So at first we have these. These are often referred to as the Great Observatory. So Hubble is the first one that went up there. It observed in the optical and out to UV and the infrared. So it sees already more than what our eyes can see. And then there's also this Chandra, which is an X-ray telescope that helps us see the universe in X-ray. This very energetic, very rare events can be captured with it. And Spitzer goes the opposite direction. It goes down to the lower energy stuff, but it sees in infrared, all the way out to far infrared, I think. So it helps us to see things that the red infrared camera that was floating around that can see, but also emission from dust. So we see things that are hot, but not as energetic as black hole mergers. Those are X-ray stuff. But One important reason why we put things in space is because of the atmosphere. So we have an atmosphere, great for us, but bad for telescope because it's actually a very thick layer of gas standing in between our eye and the universe. Everything that passes through the atmosphere, the atmosphere take a toll. So and this chart that I just added to the slide here shows you the narrow rainbow in the middle is the visible light. So the things that we see every day, it passes through with very little problem. Like some wavelengths are susceptible to water molecules. That's the worst. But also if you go to higher energy, like everything going to UV, more energetic stuff like X-ray, even more energetic stuff like gamma ray, they're all shielded by the atmosphere. So we are protected. We don't get those things directly shoot through us, but we can see them on the ground. And on the other end, we also hardly see infrared, especially far infrared, because the atmosphere is pretty good at shooting those as well. Again, it's a thick layer of gas compared to the rest of the sparse universe. So putting telescopes into space, it doesn't get us any closer to the sources because we are slightly closer, but the things are still far away. But by getting out of the atmosphere, we don't have them in front of us anymore. So we can just look straight at the stars and the starlight just come to us. So that's why we put things out there. Okay, so this is some images to show you, what Hubble Space Telescope has taken before. So these are some things are closer to us, like the Crab Nebula and the Ring Nebula, but also there are things really far away, like a galaxy. We live inside a galaxy, and there are many of them out there. So we'll talk more about that in just a bit. Okay, so this is an early design of the James Webb Space Telescope. I know you spent an hour in this room already, and you probably have seen what it looks like today when it's fully built. But the James Webb Space Telescope was first proposed in 1989. That was even before Hubble was launched. So this was one of the early designs. And I have to say, it looks futuristic to me today. And I have to applaud the engineers or the designer who designed it way back in 1989. They were the ones who are really living in the future. And of course, this is an early design concept, and it has been modified a few times until the full JWST that we see today with like 5 layers of sun shield instead of 1, and then also with a much bigger mirror than this small thing. But still, the design is there, and it's been amazing. All right, so I will talk more about why is it so amazing that they proposed this way back before Hubble in just a bit. So why study infrared light? You see, we see plenty of things in the visible light wavelengths. I see you, you see me in visible light. But these lights or electromagnetic wave don't care about how our eye work. These are just natural phenomena, waves traveling through the electric field and magnetic field. But they also extend to beyond the range that we can see. There are longer wavelength stuff like infrared, or there are more energetic stuff that might harm our skin, like UV, or even energetic stuff more energetic photons that I mentioned earlier, like X-ray and gamma ray. So infrared works like this. These are animals that we see, well, meerkats and the crocodile. I didn't pick them, someone else did. But if you look at them in infrared, you really see the difference. And the kind of difference I'm talking about is temperature here. See, meerkat is warm-blooded animal, and crocodiles are not. So that's why they show up differently. Hotter stuff emit more infrared light, and cooler stuff emit less infrared light. So I know there's an infrared camera floating around. It was fun to play with. You can actually see things through it. So I saw earlier that you can actually see your breath trapped by your mask. So when you breathe into the mask, your face looks brighter, and then when you inhale, it goes cooler. So that's something you can check out. But infrared is amazing in astronomy as well. So by being able to look into the universe through infrared, we now have this whole new window that allowed us to see multiple things. So we get there. So let me just back up a little bit and say that we can always break light down into a spectrum, okay? Just like breaking things down into a rainbow, that's one example. So on that table at the back, there is this grating that you can later take and play with it. So that is a tool that can help you break things into a rainbow. So you can see it for yourself later. Okay, but here is an illustration. So in the middle, there is this very narrow band of visible light that is captured by Hubble, of course. And in the past, we have Spitzer that goes out to infrared. So in the middle is where the James Webb Space Telescope will operate. So it's quite a wide range of infrared that we don't used to have a telescope at that sensitivity to study the universe. So it's already itself a very important instrument. but also it will deliver very, very superior resolution as well. So that will be much better than what we used to have with Spitzer. And you can see this in this figure. So on the left, well, this is, I have to tell you what this is first, right? This is the roof. If I show something nice, I have to tell you what that is. So this is the Eagle Nebula, or sometimes the media picks it up as the pillars of creation. So very nice. Stars born from this. This is a dense cloud of gas, and this is what we need to form stars. When gas condense and then they turn on and then they start burning hydrogen, and these are stars like our sun. So this is a very active star forming region. So on the left is what we see with visible light. You don't see much except for the cloud structure, because a lot of things is obscured by the light, by the dust in the foreground. What we are seeing the dust in visible light. And on the right is the near infrared image, also from Hubble. And you can already see through the thin layer of dust there. You can see these little bright dots. These are stars. Every one of them is like our own sun. Stars burning hydrogen, and maybe there are planets around them as well. And then one step to the right, the one that looks kind of red, is far infrared image from Spitzer. So it's not a telescope right now. You can already see the resolution is lower than Hubble, but we're still learning an incredible amount of it, because in far infrared we can see, well, thick cloud of dust. So we can know where the dust is clustering and maybe also figure out how hot they are. So, but this is one way to illustrate why it's important to study the universe at different wavelengths, because, well, we like how it looks in infrared. It's this nice picture, but we're not limited by just the range that our eyes can see. Now with detector, with space telescope, we can also see things that our eyes cannot see, but the full spectrum. Okay, great. So let's explore the early universe with JWST, which is the part that's my most favorite science. Let me put it that way. I get so energetic about it. Okay, but before we get there, let me first tell you how the universe works. So here is a simulation from the illustrious collaboration made in collaboration with NASA and friends. So my colleagues make this, I didn't do it. So this is just a couple 100 million years after the Big Bang. What you're looking at is just dark matter. There isn't really galaxies or stars. And this is already forming this large-scale structure, cosmic web. So this is where dark matter is located. You can see they gradually coagulate and collapse under gravity. No, what happened? You cannot take this. Okay, great. So in the dense regions, there is also where the gas was, concentrate, and then a galaxy can form, stars can form. So we're just now 3 billion years after Big Bang. We still got 10 more billion years to go. And now they're switching over to look at the gas temperature with the color here. So look at this. Those outblow is probably star forming and died, and then these energetic events just blow the gas out. And also you can see the clouds when they blow out this red color there. This is a hot gas. And of course, in the filaments, the cosmic filaments, those web, they're cold gas hanging out as well. Yeah, so this is what the universe was doing before we were there. Yeah, I can stare at this all day. Well, that's my day job, right? I think they're gradually now switching over to heavy elements. This is really important because since Big Bang, only hydrogen, helium, and lithium was created. And everything heavier than that, everything that you breathe now, oxygen, nitrogen, and everything heavier, gold, metal, silver, are made in stars and supernovae explosions, right? So these are heavier elements that we refer to, and you can see how they are now produced in stars where the dense clouds are, but they are also propagated outward after all those explosions, those gas. So it's great. See heavy elements, and they're now everywhere. Now we're back to dark matter. You can see comparing to the first few minutes or seconds of the video. Now the dark matters are more concentrated and in this spherical shape. So every one of them inside probably now hosts a galaxy. Now we cannot see dark matter with our own eye or with a telescope, but with galaxies, we can see them. So this is what we're going to see with a telescope, hopefully. So these are simulated galaxies. They are not real, but just saying this is the end product of that huge simulation. And this is how we try to connect theory into what we can see. So just something to add back, this illustrative simulation is not just animation, it's made with the physics that we know. So, we put in the physics, everything that we learn from local universe, from everything we have seen, everything we have derived, and then we dump it into a box, and then we try to evolve millions or trillions of particles, actually, trying to recreate the universe at sufficient detail, not all the details, but at some detail that we can now trust this physical simulation. All right. So this is what I call the cosmic timeline. So everything you just saw are kind of, now flattened and into this 2D space from left to right. So you see this, well, no, you're actually on the left side. So, so you are looking at it from the left, but the further out you look to the right, the further back in time you see. You see, this is important because I think this is a perfect time to introduce this concept. So when we live in our daily world, everything happens instantaneously. I look at you, you look at me. It's the same. But this intuition kind of breaks down when we go to really big scale. For example, when you look at the moon, you're looking at the moon actually a second ago because the light takes a second to come from the moon. Though the light leaves the moon and it comes to you in a second. So by the time you see the moon, you experience the moon. The moon, that was the moon a second ago. The sun is similar as well. The sun is 8 light minutes away, meaning that it takes light 8 minutes to get to us. So you're looking at the sun now, but it was actually the sun 8 minutes ago. And the thing is, it's not just light travel at the speed of light. Gravity also does the same thing. This is the universal cosmic speed limit. We can go past it. But that also means if the sun were to disappear, we won't know until 8 minutes later. So to us, the reality really is, well, the sun is 8 minutes in the past. Actually, the moon is 1 minute in the past. So when we keep looking out of our own galaxy, keep looking out and looking out, you look into this cosmic timeline, you're seeing billions of years into the past. When you see a galaxy that is 10 billion light years away, that means the messengers, the light that leaves the galaxy, it took 10 billion years of a journey. And then you now receive it with the Hubble Space Telescope, with the James Webb Space Telescope. It's 10 billion years. And that also means that photons has not been, well, it carries information from 10 billion years ago. That's why we are looking into the past all the time. So another important concept is called redshift. You see, light, especially galaxies, it likes to give off energetic radiation like UV. Galaxies emit a lot of UV light. But because the universe is also expanding, so this light gets stretched on its journey along its way to us. So energetic bluish UV light, when it reaches us, it becomes this reddish infrared light. And that's why we need an infrared telescope. That's something I hid from you earlier. Yes, infrared is interesting in itself. Infrared carries a lot of interesting information. But what we're really looking at is infrared, but originally UV. It came out of a galaxy as a UV light and it come to us as infrared. Right. Now you have seen how the universe works with that amazing simulation. And I told you how we can see it with infrared light. So this is a real image of the universe from Hubble. This is from 2014. This is the Hubble Ultra Deep Field. Every blob you see here, I got so excited. Every blob you see here is a galaxy, not a star. You live next to a star called the sun. But the sun is inside this huge galaxy called the Milky Way galaxy, which contains about, 200 billion stars, 2 trillion stars, something like that. So many stars inside the collection is called Milky Way. And every blob of this is a whole galaxy. Of course, there are massive ones like ours, there are smaller ones. But every one of these is a huge collection of stars. Many things go on, not just stars, but also there is gas in there, dust, different colors, different distances. These are, I need to look at my notes. There are 10,000 galaxies in this image. 10,000. How big do you think this image is? I know it's hard, so I give you the moon for scale. That's the moon in our sky, not cosmos. This huge field here is cosmos. The one I showed you earlier is Hubble Ultra Deep Field, HUDF. Can you spot where it is? It's right there on the left. That's the Hubble Ultra Deep Field. It contains 10,000 galaxies, the ones that we can see. So what I'm saying is, it takes a lot of time for Hubble to go that deep. But when we do, when we stare at a blank piece of the sky, we see countless numbers of galaxies. And so with Hubble, with James Webb Space Telescope, we will go deeper into a small area like that. So we'll see more than 10,000 galaxies, maybe 20,000, maybe 50,000. We can see more faint galaxies. Yeah, just for scale. And of course, in the future, if we're able to survey the whole cosmos field at that depth someday, actually, we have plans for that. We're going to find, I don't know, 100,000 of galaxies, maybe 1 million, so many. And we can study them too. So let me give you a taste of how we can study them and extract information from it. So back to the Hubble Ultra Deep Field. Here is one. Yes, this image is also incredibly high resolution. The whole thing, I think, is 6 megabytes. But one of these galaxies, is like us. Looks like it's a spiral galaxy that has spiral arms. Great. So big one, maybe. We also see galaxies that are stuck together, maybe a cluster. Just a small patch of that image. This is actually not the full image too in the background. This is part of the full image, and we can still just zoom in and keep seeing. There's incredible amount of detail in there. People get PhDs out of studying this image. Well, I didn't do that. Yes, and this is another one that is really, really red. And remember I tell you about redshift earlier. So these galaxies could be red, but in fact, we think it's incredibly redshifted in a way that it's so far away from us that it is one of the highest redshift galaxies. This might be going into the first 10% of the universe's history. That's why it's really important that we get a census of galaxies, and we study them, we sort them. So let me see. So if we do that, every point of there is a galaxy, let me remind you. And this is what we see, because we cannot really go out of the Earth, go out of our Milky Way, or tour around the universe. We can't do that yet. Maybe someday in the future. But as a theorist, I get to take you out of there and give you a different perspective. So this is my crappy side view of that field. So, I'm a theorist, so I don't care about aesthetic, but I can show you a different perspective. So you are now on the right side of the screen. This says you are here, like you're at a shopping mall. But now you're looking into the field a little bit from the side. So you see every point is still a galaxy, and bigger galaxies are purple and with a bigger point. But you see the idea. Now we can construct a universe in a view, well, from a theoretical point of view, where the galaxies are physically. So we can now look through it, fly through it. And now you can look back in time. The further something is, the longer it takes for the light to reach us. And then now we have these slices of the universe from the past. And we can now put together a full story, how the universe begins, how objects first start to form, and then how they evolve over time, how galaxies merge, how galaxies grow in size, how stars gradually grow with more metal and then later on become smaller and less blue, that kind of thing. Everything we can extract from it, we can put together. And this is how we can look back in time really with the James Webb Space Telescope. And I forgot to mention at the beginning, I got a PhD for making predictions for JWST. So that's what I've been doing, hiding in a lab room for the past couple of years. So yeah, I'm really excited. Okay, so this is the time machine aspect. You can ask more about it later. But there are 4 instruments on the telescope that it carries, that we will use them to study the universe. So this is not like an iPhone. So it doesn't just have a camera with 3 cameras. Well, a camera with 3 lenses. But really it is a 4 instrument system. So NearCam, or the near infrared camera, works the most like your iPhone camera. It has a CCD, I think, and then imaging. Of course, it will take pictures in infrared, but it does imaging. The other 2, all 3 that starts with NIR are near infrared stuff. So we have also NIRSpec and NIRISS, which, like I mentioned earlier, it will help break down the light from distant galaxies and help us see their fingerprints, their spectra, what is in there, what kind of chemical composition is in the atmosphere of a galaxy or of a star. We can see those things too. And then also mid-infrared is really cool. MIRI. So this is the mid-infrared instrument that will help us look further into the infrared. And for me, it will help me see galaxies at higher redshift even. And of course, for other galactic physicists, they can also see dust, see through some dust, and see stars forming inside. So this is the field of view of JWST lay over a galaxy. So these instruments are looking into this universe is sort of in this layout. The reason why I have to flash this really quickly is because in the next slide, I'm going to show you how some of our teams are trying to make the most out of JWST by leveraging on what we call a parallel mode. So JWST has these 4 instruments, and you can use 2 or 3 of them at the same time. So we get really clever about that. But just kind of have this layout imprint in your head for a second. And this is it. So something from a real observing team that I'm part of. This is the SEERS survey, which we will go back to survey one of the very well surveyed patches of the sky. So you saw Cosmos earlier. This one is called EGS, it's the extended growth strip. So this is one of the fields that was surveyed all the way back since 2004. And then we just keep going back, go deeper, go more detail, go multi-wavelength. So you can see what happened here is, what I'm trying to show is the purple ones is near CAM, and then the red one is near SPECT. And then we're also using MIRI, shown by the green. So we're trying to be very clever here by rotating the telescope and tiling our pointings to make sure we get the maximum exposure times and all the telescope stays within the field. Well, the same telescope, all the instruments stays within the field. So that's what we were doing. So we try to squeeze the most amount of science we can out of only 68 hours of observation. I know no one usually on a daily basis take a picture that was 68 hours of exposure time, but this is how long it takes to observe the universe, because these galaxies are incredibly faint. So even with JWST's superior sensitivity, it still takes tens of hours to get these galaxies to show up. And if we want more detail, well, then we'll have to do even longer exposure. So another one I want to show you is called WDEEP. It's the deepest survey that JWST will do within its first year after commissioning. So this is important because on the right side, just to quickly highlight SEERS, you saw from the last slide, is going to see that in the box. So this is a simulated image. On the right is how much deeper we're going to go with WDEEP. It's really important because WDEEP can now help us see galaxies that SEERS cannot see. It really just an illustration for how you can see extra galaxies showing up into a rather noisy field. So this is why we're going to go over 100 hours of exposure time here. Really excited about it. Again, this is a simulated image. JWST has not fly yet, but hey, within a year, we are going to see the universe at this depth, and we are going to understand how they formed. So ultimately, we are going to create a flipbook for galaxies. How it formed in the early days. How does it get from those small little guys, hard to see guys, to the big one that now will live inside? This also implies what our own Milky Way has gone through. We cannot really see our own Milky Way into the past too far in the distance because, we live inside it. But by looking into a distant universe, we can see what the universe was like in the past. And now we can stitch together a whole history. And by that, it infers to also what our Milky Way has gone through in the past. So this is very important. It will also help us discover one of the first galaxies formed in the universe. This is a real image of a high redshift galaxy, what they look like. This is at redshift 11. This is going back to the first 10% of the universe's history. Our universe history is about 13.8 billion years. This is going back to about the first maybe 500 or 600 million years. So really close to the beginning already, and anything further than that's probably nothing too much in there because the universe was still hot, nothing was forming. So we are really good at getting, into the early days, seeing really the first batch of things form. Kind of proud of that as human. We're doing it. But also, JWST will be able to help us understand black holes. I know black holes are black. You can't see directly from them because they don't really emit light. But black holes do interact with the surrounding environments. You know, a galaxy is a complex system. It's not just stars. Galaxies also have gas, hot and cold gas, and different things. Also, black hole is part of galaxies too. And when the gas fall into a black hole, or when black hole merges, it emits something. It accelerates particles, and when something gets accelerated, it emits light. So that's what happens. So JWST will help us understand how black hole forms as well. So that's actually my program. Okay, so there's so many things going on as well in the nearby universe. We can understand how stars formed and died. You know, if we can understand gas clouds better. Gas clouds meaning, you know, a cloud of gas. They're hot. They have to gradually cool, and then they can finally condense, and then star will form inside of it. So we need to get that bit of information as well. Of course, this is also one example. Just nice image to stare at, but it's my job to get the science out as well. So molecules forming in star-forming regions. Yes, well, as I mentioned earlier, there are many things that help us understand star-forming regions. Molecular gas, metal, you know, metal also means, you know, there's oxygen and other things. So these are all important elements for forming stars. Imagine you need to get your recipe to bake cookies. Now we try to bake stars. Well, first I have to find the recipes, where they are, and then predict where stars can form. So that's what happens. Right, now let's dive back into the telescope. I've shown you, you know, enough about the universe. The telescope is important too. It's our tool, it's our eye to the universe. So it's an engineering marvel itself because, well, I get an iPhone every couple of years. It's a small upgrade. But every time when we put up a space telescope, it is a different beast. It's engineering from the ground to top. It's designed with very different purposes in mind. For example, when they put up Chandra, it's an X-ray telescope. The optics work completely differently than Spitzer, which is an infrared telescope. So these are all, you know, not small modification of the same telescope. They all kind of look the same from the outside, but in fact, they have to be designed from scratch every time almost. So James Webb is the same. You see, all the past telescopes we have kind of have the same theme, at least. There's a tube, there's a mirror inside, there's like wings. No, they're not wings, they are solar panels. But James Webb has a huge mirror that I'll get to in just a bit. This is it. Well, Hubble, it was 2.4 meter, slightly taller than our door. James Webb has a 6.5 meter mirror. We can't launch that thing in one piece. We can't really launch it without folding it up. So that's why it's a huge mirror. Which is back to how James Webb is really a technological marvel. It's because they have to keep inventing things to make it happen. So for example, James Webb has to stay cold because it's an infrared telescope. You see, you and I emit in infrared. Everything has a temperature, emits in infrared. So if a telescope itself is hot, it will be looking at itself. So in order to make an infrared telescope that sensitive, you know, we are talking about starlights that takes hours, hundreds of hours to show up in our imager. We need the telescope itself to be really cool. We need a shield. And this is one of the things that we're really engineered from scratch. And this is part of the reason for the final stretch of delay from the past 2 years. But really, every part of it, how the mirror can fold and everything. I'll show you a little video that shows how it unfolds. But really, this is the reason why it took so long. I also was waiting. When I first started my thesis in 2018, it was supposed to be launched in 2018, and I had faith in that. I did, really do. That's why I put my whole thesis on this telescope. And then it got delayed to 2020. So, well, I keep working, so I wrote more stuff about it. So just keep that going and keep that going. Also, our engineer worked very hard and to make sure everything works. Another thing to mention now, but you see later, is that the telescope will be so far away from us. We're not putting it in low Earth orbit. No, we can surface the Hubble because it was orbiting around the Earth, and we had the space shuttle at the time. But now we are going to put it really far away from us, like 1 million miles away. So we can't really surface that. we have to keep it cold. That's the important part. We have to make sure everything works. Once it's launched, there's no going back. And I think at NASA, we say failure is not an option. So it has to work. Okay, so this is the moment that makes me really feel this is coming together. This is a folded up JWST. I've only seen this in animation before this came out. So JWST is now all folded up, actually already arrived at French Guiana, its launch site. So you see the video shows it's kind of fast, if it's folding up, but look at the time lapse, look at how quickly the people move. This is actually, a time-lapse video. The telescope fold and later on unfold in space at a really, really slow pace. It would take 2 weeks to unfold, actually. So everyone who's doing commissioning will be, like watching paint dry. But yep, so this is the last time we see it on Earth, actually. Now fully folded up. So let me just pause this for now so I can say a little bit more. So it will go to space like this. So it'll be attached to Ariane 5 telescope rocket. It gets me every time. But we put on top of a rocket and then we'll launch it to space. And then shortly after we launch it to space, we have to deploy this solar panel so it gets power from the sun. And then it will also have the high gain antenna fold out in just a second. Let me see if I can speed this up. Right, guess we're gonna watch this in real time then. No problem, I'm trying to speed this up a little bit, but no. Right. I'm just going to go past a little bit. Anyway, you probably have seen the full video a few times already today. The thing is, we are going to launch the telescope on the 18th of December. This is the launch window we get. So we didn't pick it, but you see why it's important. Well, it's the 18th at 7:20 a.m. So tune in to the news. It will be everywhere. So we're counting down by the days now. In the past, we count down by the years, by the months, and then by the years again. Because of the delay. But now we're counting down by the days. When I first made this talk, we were counting down about 45 days. Now it's just 30-something days, a month with a few extra days, 34 days, 33 days, whatever. It's going to launch very soon. But the neat thing is, because we're launching it on the 18th, so by the time the sun shield fully deploys, guess what? It's actually exactly a week after its launch, so it will be Christmas Day. So that will be my Christmas present. We're going to have a fully unfolded sun shield. It's going to keep JWST cold, keep it functional. So, it has a SPF of 1,000,000. So the sunlight's not going to go through it. It's going to keep the whole thing really, really cold. Okay, so I think this is the time I'm going to scroll past a little bit more. I think this. Okay, so now you're looking at what is happening about 12 days. You can see the clock in the top is, going by really quickly. But in real life, we'll have to go through this in real time. So you will see the telescope actually unfold very, very slowly, in the real deal. So these take a whole day to do. So this marks the 2 weeks line. And hey, in 2 weeks, we'll have a fully unfolded mirror. So Happy New Year. That it is. That's my New Year present, or my New Year resolution will be to use the telescope to get more science out of the universe. Okay, and this is the bottom of the telescope, and it will enter this orbit. So that moon is not to scale in size, but for distance on the lower right. Oh, darn, it's gone now. Oh no. Just to show you to scale how far away JWST will be at. So it will go past the moon in the first couple of days, but really it is this far away from us, the moon and the Earth, to scale anyway. Okay. So this is the, let's see if I can get back to the launch sequence. Okay, so yes. These are the things to look forward to after launch. I think JWST, the official YouTube account, put out a video called 29 Days on the Edge. So we didn't call it 29 Days of Terror. They used to do that with Mars mission. Mars mission do it with 7 minutes of terror, because you lose contact with the Mars rover as it enters Mars atmosphere. You can't talk to it when it's going through that. So we will actually stay in contact with JWST this whole time. We have 29 days on the edge, waiting for good news. Okay, there's so many parts that has to be deployed and go in place. Like, you saw the sun shield has to unfold, and then what I did not talk about is the secondary mirror also has to come down from the tower. As you can see from the 1, 2, 3, 4, 4, and 5th image here, there's this secondary mirror that has to come down, and then it's kind of hover above the primary mirror. So that's also an important milestone. So we get confirmation one after another for 29 days, if you think about it that way. So on the edge waiting, but not anything bad. That's important. Okay, so JWST will be doing this little dance not around the Earth this time. It's going to be so far away in this called second Lagrangian point, which will be staying in the Earth's shadow as the Earth orbit around the sun. So you see, the Earth goes around the sun, and then JWST will be like on the far side of the sun, or in Earth's shadow, basically, because it has to stay far away from the sun and the Earth to stay cool, and also not observe this noise, infrared. So it would do this little dance along with the Earth and go actually orbit around the sun with the Earth, and that's the plan. They'll go around and around and around. Yes. And we're going to communicate with JWST through the NASA's Deep Space Network. So I think it's the DNS or DSN. Right. So there are these 3 gigantic dishes strategically located at, I think Goldstone is one of them, and then Madrid, and then Cambria. So they will give us 24 hours coverage through, just looking out, receiving basically information from James Webb, and also sending up instructions. So the data, we're talking about gigabytes of data, will come from the telescope down to the network receiver on the ground, and then it'll be routed through Goddard Space Flight Center. I won't touch them, but I'm just happy that I'm close to them. I work at Goddard. And then they'll be rerouted to the Space Telescope Science Institute in Baltimore, which they actually operate the telescope. So that's where the telescope operation room is at. Okay. Let's see. So Webb is also an international collaboration. The observers, astronomers around the world are all welcome to submit proposal and propose how to use the telescope. All the teams are actually very international. I have collaborators in the Netherlands, in France, and in, where's she now? In Italy. So it's great because the telescope itself is also a joint venture between our space agency, NASA, and also the European Space Agency and the Canadian Space Agency. So it's great for working with astronomers around the world, trying to solve the universe mystery together. And of course, just back to all kinds of science JWST can do. I didn't get to talk too much about the other kind of science because I get too excited about the early universe, but James Webb is also well equipped to study how planets formed, and to study planets' atmosphere, also study stars, and study, other things. But this is, now we're back to the early universe image. There is the Hubble Ultra Deep Field again. So one thing I forgot to go through in my talk is, when Hubble Space Telescope launched in 1990, we did not know we're going to see the Hubble Ultra Deep Field. We did it the first time, the regular Hubble Deep Field in 1995, and then the Hubble Ultra Deep Field later in 2014 with this longer exposure time. We really get this stunning image without knowing what is in there. So it's important to know that we're going to launch Hubble now. Well, of course, Hubble was proposed before we even have the deep field, so it was even more future-looking. Now it sounds for JWST. It was proposed without us knowing that the universe is full of galaxies, and now we know it is. But we also don't know what JWST can see. That is the most exciting part, I think. You see, well, Hubble tells us what is in the universe, but back then we did not know the universe was full of galaxies. So this time we have some knowledge about the universe, but we're also looking for the surprises we're going to get from JWST? We don't know. Maybe when we do an even deeper image, we found more galaxies than we expected. Maybe the universe doesn't work the way we think it does. Well, then we get to spend more time to study the universe in the future to get all the answers we want. Maybe another space telescope. So it's important to get involved. So there's the JWST website. They remade it in the past month. It's really amazing now. They have this animated countdown with the rocket launching with JWST inside. So we are, I took this screenshot from last night. So we're now just 33 days away from it. I can't be more excited about that than, it's just a little more than a month and it will fly. We're waiting for this for so many years now. Also, you are in one now, but there are so many more of these JWST community events around. I know a lot of them are actually virtual. So I grew up in Hawaii, so I just looked, and then I found, well, my local library, Kaimuki Library, is also doing one, so I might be able to just pop into that one. I don't know yet, but for you folks, feel free to pop into more and see. Maybe you next time will run into a planetary scientist and tell you how JWST can help them understand planet formation and planet atmosphere. And I will take questions from here. Yes. Go ahead.
Why do you need a sun shield if it's in the shadow of the Earth?
Right. So that being there helps a lot already, but also the sun's radiation will actually reach the telescope as it dance around the orbit. Plus, the Earth is actually a really bright infrared source. Yeah, but the sun shield really will keep it cool. And on top of that, something I did not mention is it has an onboard cryogenic cooler, specifically for the mid-infrared instrument. So it has to be even, so the sun shield is part of the passive cooling, but there's also an active cooling element to it to make sure the telescope operates at the really low 50 Kelvin temperature. So if you know Kelvin, well, it's the absolute 0 Kelvin is negative 273 degrees. So it's really, really cold, 1 degree Celsius. So I need to figure out what is that in Fahrenheit. Yeah. Yeah. A question from the back? Good question. I speculate you probably know. Yes, so the question is, can it detect water vapor in the exoplanet atmosphere? So we think it can. And in fact, there is proposal trying to do that already. Again, water vapor kind of act against us in this planet, right? Because we want to see the outside. But when light from a star pass through the planet's atmosphere, some of that light will get taken out the same way and show up in our spectrograph. So what we'll be looking at is the spectrum, the rainbow of a starlight, and looking at where the light is missing. If that wavelength corresponds to the water molecule, then we know there is water in the atmosphere. So that's how we think we're going to detect that. That will be quite a challenge. So we don't know yet. We'll come back and tell you if they successfully detected that. Great. Yes.
What elements and compounds are we receiving from our sun?
Now, what was the first part of the question again?
What elements?
Oh, what elements?
Compounds are we receiving from our sun?
So what elements and compounds are we receiving from the sun? So I don't think the sun is actively blasting substance at us. So the sun is very energetic, so it's burning hydrogen mostly. So we get a lot of electromagnetic waves, a lot of light and multiple wavelengths. We also get some charged particles, some electrons and protons. And those are actually harmful to us, and those get redirected by the Earth's magnetic field to the poles, and that's why you get aurora. But I don't think, not that I'm aware of, the sun is dumping a lot of stuff at us. Yes?
What kind of things do you think you're going to be able to learn about black holes?
What kind of things can we learn about the black hole? So there's several kinds of black holes out there. So in the center of every galaxy, like the one we live in, there is a supermassive black hole by calling it supermassive, I have to give context. So our sun, one sun is one solar mass. And supermassive black holes typically go from the range of 10,000 solar mass. So 10,000 suns get lumped together as supermassive black hole. That's the smallest, all the way out to maybe 1 million. So these are very common, we think, in the universe. And we can't see them directly most of the time because black holes are black. But when they accrete stuff, when things fall into them, these particles get accelerated, and sometimes they emit in all sort of stuff like radio wave to X-ray. So this is one way we can detect these objects. They are often referred to as quasars. So by looking at quasars, looking at them, we can see how many of them are out there. But there are also other ways we can study black holes. For example, when black hole merges. So you hear about this a lot in the past 2 years, because when black hole and black hole merges, you see gravitational wave as well. So that's what LIGO is detecting. But we also sometimes look for an optical counterpart. So for example, if it's not black hole mergings, but instead neutron stars and neutron star merge, they will have this light coming out of it as well from the same spot. So if we detect something from the gravitational wave, then we go look in the same direction to see if we see light as well. Then we see if they have an optical counterpart. So that's another way as well. Yes. Good question. So I told you about how it will be routed back. So from there, I think it will go to the observing team that proposed to do the observation. So the telescope operates as follows. It operates 24 hours a day. We can't go beyond 24 hours a day because that's all the time. So teams of observers has to put in proposal to say what we're going to learn from looking at these things, and then they are responsible for analyzing that data afterwards. So hand them the data. But usually what happens is we have to reduce the data, meaning that we go from the pixels. Every raw pixel is full of science, but they are not very meaningful without processing them. So one way to go is to put them into images. So figure out the color. The multicolor images you saw earlier, they are actually, well, it doesn't really work like a camera, but instead, so we have to take pictures of the universe through different filters. And for example, NearCam has a set of 8 broadband filters, and we have to sort of put those information together and figure out what color is that pixel, and then put together a whole image. And when we do a large survey like this, remember I showed you the tiling. So the telescope itself, look at a tiny little piece of the sky. It's like a pinhole. But if we want to see a large image, we have to find a way to put these little snapshots together, to tie them together to form a bigger image. So that's also a really hard task. Yep, so hours of my work after the launch. Yes?
What's the expected lifetime for the Webb Space Telescope?
Good question. So the question is, what's the expected lifetime of the telescope? So the nominal lifetime, short answer to you, is 10 years. And there is a huge error bar to it, meaning that it can go up and down. And one of the deciding factor is how good the launch is. You see, when JWST is launched with the Ariane 5 rocket, it goes into space, and then it has to be on the right trajectory to the second Lagrangian point. So somewhere along the way, I think one of the burns will be using JWST's onboard fuel. So if the launch itself is perfect and the fuel itself is being mostly unused, then we'll have more fuel when it arrives at L2 that will help keep JWST in position. So the thing is, the second Lagrangian point where JWST will be at, it is not a stable point. It requires a small bit of fuel to keep it in there. So it has to do this little dance around that point along with the Earth, around the sun, but it requires a little fuel. So if JWST run out of fuel, it will drift away. Well, that's the end of mission. But yes. But so it all depends on how much fuel lives in the tank. So well, in the worst case scenario, if we have a terrible launch and we have to use a lot of fuel to get JWST back to its track, then we might see less than 10 years. Hopefully not too much less than 10 years. But if we say we save all the fuel that we want, the launch was almost perfect, then we can actually see upward of 15 to 20 years. But of course, that's only the thing that we now all care about or foreseeable, like, the fuel. But there are also so many other things that could fail over the next 20 years. For example, the sun shield, the detector themselves. So also the cooler, important for the MIRI. If the active cryo cooler doesn't work, then we lose MIRI for good. So there are multiple parts that determines the lifespan of the telescope. But I think the fuel is the biggest part. Yep. Yes.
The telescope start to unfold on its way out, or do you have to wait till it gets to its point, then unfold?
Good question. So will the telescope unfold on its way out? So the whole animation you saw earlier, it happens on the way out. So we have to establish connection with the telescope after its launch for 30 minutes. And then we can send commands out and have it unfold. So there will be a period of time where it kind of actually just sits and doing nothing. So it does some of the unfolding. I think the sun shield has to unfold first because it helps the telescope cool. But then the telescope won't finish unfolding because it has to keep cooling just by doing nothing, just sit there for a couple of days. And also, I learned something new a couple of days ago. It's called outgassing. So all the material you made on Earth, everything you make, has some gas particle inside it. So when that thing get out to space, space doesn't really have an atmosphere. So the gas that get trapped inside the material, we have to find its way out. So that's called outgassing. You have to, everything that get launched into space has to sit for a little bit to let it outgas, and then it will become functional and operational. And then it does its own thing, unfolding along the way. So it would take only 15 days to get to L2. So by New Year Day, New Year Day, we also have the primary mirror fully unfolded. And Happy New Year by then. and then there will be another 6 months of commissioning. So unfolding is just the first part of the story. This 18 segment. How did I not say this earlier? So the mirror is made out of 18 segments of gold mirror, right? They don't yet work together. So it's in the commissioning process. The super clever engineer, actually, someone quote there, the wizard of smart, will have to align these 18 independent mirrors to make them function as one. So they can focus light to the sensor as they are designed to do. So yeah, so the first 29 days, it will unfold on its way. But then once it arrives there, we have 6 more months of work to do before it can deliver science to us. Right? Any more questions? Hopefully not Terra, just good news. Yeah, thank you. So I learned that there is the first thing it will do is actually the early release images, so not even science. So there's this program that's internal to Space Telescope Science Institute, I think. They would just use the telescope to take amazing pictures of the blank sky to see galaxies, to see planets, and then they will release that firsthand. So everyone knows it works, it's beautiful, it's worth the money. And then we'll do science of it. Right. Thank you. Right.
Thank you all for joining us.
Thank you. No. This is one organizing this in Texas.
Yeah. So you can hold this. All right. So there's the camera. All right. So can you see me? Yeah. So when I breathe out, can you see the change?
So the other reason you're talking about the telescope using this kind of work States that what kind of radioactivity you can. So, okay, first question. So, can you see it? Can you see it?
So one of the wonderful challenges about astronomy is that we have to imagine something so we can go look for it. But nature has this way of being even more creative than we are. So we have always been surprised by what we see in the sky. That's why building a telescope has always been interesting. Every time we build a better one, we see something we never imagined was out there. That's been going on for centuries. This is the next step in that great series of a bigger, better, more powerful telescope that will surely surprise us in some way that I can't tell you.
So the James Webb Space Telescope at its core is designed to answer some of the biggest questions we have in astronomy today. And these are questions that go beyond just being science questions. They're questions that really get to the heart of who we are as human beings. Questions like, where do we come from? And how did we get here? And of course the big one, are we alone? To answer the biggest questions in astronomy today, we really need a very big telescope. And the James Webb Space Telescope is the biggest telescope we've ever attempted to send into space. It really sets us up with some really big engineering challenges.
It had never been done before to build a big unfolding telescope in space, because we knew we needed something that was bigger than the rocket to achieve the scientific discoveries that we wanted to make. We had to invent a new way to make the mirrors, a way to focus it in outer space, several new kinds of infrared detectors. We had to invent the big unfolding umbrella. We call it a sun shield.
Webb has 4 broad science goals.
To detect the very first stars and galaxies that were born in the very early universe. So this is a part of the universe that we haven't seen at all yet. We don't know what's there. So the telescope, in a sense, is going to open up this brand new part of the universe, the part of the universe that got everything started.
To search for the first galaxies that were born after the Big Bang.
The first stars and galaxies are really the big mystery for us. We don't know how that happened. We don't know when it happened. We don't know what those first stars were like. We have a pretty good idea that they were very much larger than the sun and that they would burn out in a tremendous burst of glory in just a few million years.
To watch how galaxies grow and change over time.
We have questions like how galaxies merge, how their black holes form, and how gas inflows and outflows affect galaxy evolution. But we're really missing a key piece of the puzzle, which is how galaxies got their start.
To find stars and planets born inside dusty clouds, and to help in our search for life in the universe.
So astronomy is one of the most observationally based sciences we've ever had. Everything we know about the sky has been a surprise. The ancients knew about the stars, but they didn't know they were far away. They didn't know that they were like the sun. Eventually we found that our own galaxy is one of hundreds of billions of galaxies, and that the universe is actually very old, but not infinitely old. So that was a big surprise too. Einstein thought, of course, the universe must have an infinite age without a starting point. Well, he was wrong. So our intuition has just been wrong almost all the time. We're pretty confident that we don't know what we're going to find.
As an astronomer, one of the most exciting things about working on a telescope like this is the prospect of what it will tell us that we haven't even thought of yet. We have all these really detailed science questions that we'll ask, that we know to ask, and that we'll answer. And in a sense, that's what science is all about. You know, in answering the questions, we come up with more questions. So there's this almost infinite supply of questions, of things that we have to learn. So that's why NASA builds telescopes, is really to get to this fundamental part of who we are as human beings. You know, we're explorers, and we want to learn about what our universe is like.